check this out. We've got something really fun today. This is so amazing, math. Oh man, again?
10.1, area under a curve. We want to be able to calculate the area under any curve, and we're going to define this as the area underneath the function, but above the x-axis, and bounded on the left by some lower bound, and bounded on the right by an upper bound. Now, if the function is below the x-axis, then it's still between the x-axis and the function, but this will come out calculated as negative area. And if we want to consider a positive area, we'll have to correct for that. Let's start off with an easy example, the area under a linear line from 1 to x. Now, I did draw this from 1 to 4, but this upper bound here, we want to be just x, just a general x. So it could be 4.5, could be 5, could be 3.9, just x. Okay, we have the area of a trapezoid already. It's height times a plus b divided by 2. Now this would be turned on its side so that the height is actually here and the top and bottom are here and here. Okay, so we have 1/2, that's fine, and the height. Now the height will just be x, wherever this thing ends, minus 1. That would be the distance in between x and 1. And then we have a plus b. Now we do know a, it's 2, but we don't know what b is. B is just whatever our y value is here at this point x. So our b value is just going to be y, so that's why I put y right here for b. Then I don't want y here, I'm going to sub it out using this equation, x plus 1. So there it is. And simplify that and multiply it out, and this is the area of this trapezoid. Now, what's really crazy about this is that if we look at the original function here and we take its antiderivative, we get the area equation. Or working backwards, if we take the derivative of this area equation right here, we get the function. Let's see how this would work with some actual numbers. We want to find the area under the curve from 1 to 4. Now, first of all, you might be saying, hey, this isn't a curve. Well, a curve is just a generic term we use for any function that we're working with. This example is so easy, we can actually just count up these boxes to find the area. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then these two half ones will make 10, and this one here will give us 10.5. So the whole area, 10.5. Let's use the antiderivative found in the previous example. So we saw that the derivative of our area equation was the function. So we'll just use the antiderivative of that. The area was equal to 1/2 x squared plus x minus 3/2. And we want the area here at 4 as our upper bound, so I'll put a 4 in here. So 1/2 4 squared plus 4 minus 3/2. And 4 squared is 16, divided by 2 would be 8, plus 4 minus 3/2, or minus 1.5. So 12 minus 1.5 does give us 10.5. Now this is crazy. Why would the antiderivative of the function itself have anything to do with the area? Why is the area the antiderivative? We're going to find the area using an infinitely small trapezoid. So here's our setup. Here's some curve f of x. And we're going to say the area from 0 to this value here, x, is going to be our area function. and it's going to be a function of x. So it depends on how far or close x is here. We've got this extra area here, and that will be at x plus h. And this area here in gray, that will be our area at x plus h. But the way that we defined this was the area from this point back to 0. So I can't say this, or I'll get the whole gray and red area. So I'm going to subtract this area off, just so that I'm left with the gray area here. Okay, so that's fine. And we can say that the area x plus h minus the area at x is this gray area. And we're going to approximate the gray area with a trapezoid. I mean, it even looks like a trapezoid. It's just this edge here that's actually curved, and the trapezoid will be straight. So it's only going to be an approximation for now. And let's do the area of this trapezoid. So we've got the height, which would just be from here to here, and that would be h. And then we have this side here, and that would be f of x, because that would be our y value at x. That will be f of x. And then this side here, and that will be f of x plus h. And then it's a trapezoid, so we divide by 2. Now, we're going to do two things. First, we're going to divide both sides of this by h. And then we're going to take the limit as h goes to 0. Now, as we get closer and closer, h gets smaller and smaller. This trapezoid is going to get more and more accurate until once we have the limit as h approaches 0, it's going to be actually equal to this area. So we'll do that. We'll say the limit as h approaches 0 of a x plus h minus a at x divided by h is equal to, and this h will cancel, and here we're just left with the limit as h approaches 0 of f of x plus f of x plus h divided by 2. Now on this side, you see what we have? This is how we defined our derivative for a function a. So on the left side here, this is the derivative of a. On this side here, the only h we have is right here. So if we let h go to 0, all we'll have is f of x plus f of x divided by 2. And that can be simplified to 2f of x divided by 2, and we can cancel that out. And that means that the derivative of a of x is equal to f of x. And that's what we saw in the previous examples. Now the cool thing is we can use an infinitely small rectangle to show this same thing. So using the same setup, we have some function here, f of x. We've got the area from 0 to x, and we'll call that our area function at x. We've got this gray area here, and that will be from x to x plus h. And so our area function would be area at x plus h. That would give me the whole red and gray area. So again, we just need to subtract off the red area, so we're just left with this area here. Okay, and instead of a trapezoid, which you can see is a better fit for the shape, we could use a rectangle. So like this. Now you can see the rectangle is going to be smaller, But it doesn't matter because as we make h approach 0, the rectangle is going to become a better and better approximation of this gray area until it is equal to the area. So let's set up this same thing. We've got the area of x plus h minus the area at x. And this time I'm just going to say, you know what, I do know in this picture here at least that that's going to be greater than my rectangle. So what's the area of the rectangle? Well, this base here would be h. So a rectangle's area is just base times height. So h times, how high is this rectangle? Well, that would be the y value right here. So that would be f at this x value, f at x. So there's the area of a rectangle. Now I want to do the same two things as last time, actually. I want to take the limit of both sides, and I also want to divide both sides by h. Because you can see what's showing up here. And on this side, the limit as h approaches 0 of h times f of x divided by h. We can see these h's are going to cancel. On this side, this is our definition for the derivative of a of x. So on this side, we just have a prime of x. And now that we've actually taken the limit, this is a perfect approximation for the area under a curve. So now it's equal. And there's no more h's on this side, so it'll just be f of x. Now, you're looking at this and probably thinking, yeah, but we want to find the area, and what you have here is the derivative of the area. So we need to take the antiderivative of both sides. And so that will give us the area equation that we wanted. So the antiderivative of small f of x is capital F of x. Now you also might be thinking, hey, we learned that when we took the antiderivative, we had a constant showing up. So that's true, we could have a constant here. And that's kind of annoying because that's unknown and we don't want that. So let's look at what we have here. When we're doing a question where there's the area under a curve, we probably want to have a lower bound, as I mentioned at the very beginning, and an upper bound. So we'll call the lower bound A and the upper bound B. And if I actually have the area at B, using this equation right here, that would be the antiderivative at B plus C. And if I have this area at A, that would be the area at A, which would be the antiderivative at A plus C. Now, presumably, since B is farther up here, the area would be larger and the area at A would be smaller, so I could subtract them and to get the area in between. So that would actually give me the area from A to B, and that would be F at B minus F at A, and you can see that the C here cancels out. So we don't need to worry about it as long as we have an upper and a lower bound. There's another way to think about this, and that's if we have the same setup here. So my area at B is equal to the antiderivative at B plus C. And I'm going to use initial conditions to solve for the C. So if I had my area at A, that would be the antiderivative at A plus C. And you know what? I would like that to be equal to 0. So if I put in A, I just get 0. That way I don't count anything over here. And then if I put anything larger than a in, I'm going to get some area starting from there. So this should be 0. Now if I just solve that, that would mean that c is equal to, subtract this on both sides, so c is equal to the antiderivative at a. So in that way I can put in my c value here. It would be minus f at a. And that actually gives me the same result as this. So my area from a to b is equal to the antiderivative at b minus my antiderivative at a. Now we can actually give this a try and find the area under a curve from x equals 2 to x equals 4. And here's our equation, x squared plus 2. So first we'll need the antiderivative, and that would be x cubed divided by 3 plus 2x. And I don't need the plus c because I know it's going to cancel out anyways. So my area from 2 to 4 is equal to the antiderivative at 4 minus the antiderivative at 2. I'll put 4 in here, so 4 cubed divided by 3 plus 2 times 4 minus 2 cubed over 3, and I'm just going to distribute in the negative in the same step, so minus 2 times 2. This will be 64 over 3 plus 8 minus 8 over 3 minus 4. And that would be 56 over 3 plus 4, so that's 56 over 3 plus 12 over 3, and that would be 68 thirds units squared. Find the area bounded by the curve and the x-axis for the function y equals 4 minus x squared. So you notice in this question, they're not giving us an upper and a lower bound, so we're going to have to sketch this to figure out what area they're talking about. Now I do know that this is a parabola. It's got a negative leading coefficient, a y-intercept of 4, so it opens down, and it's got x-intercepts at -2 and +2. So the area bounded by the curve and the x-axis is this area right in here. So that means I want to find the area in between -2 and +2. So first I need the antiderivative of this, and I'll just call that capital F of x again. So the antiderivative of 4 is 4x, the antiderivative of minus x squared is minus x cubed over 3. So our area from -2 to +2 is equal to the antiderivative at 2 minus the antiderivative at -2. Let me just put in these numbers and subtract them. So 4 times 2 minus 2 cubed divided by 3 minus 4 times -2. And if you get confused with this negative sign, then use brackets. So maybe I'll do it with brackets this time, and then distribute that in as a separate step. So minus -2 cubed over 3. Okay, so this would be 8. This will be minus 8 thirds. This would be -8, but distributing in the negative here will become +8. And this one here is -8 thirds times this negative makes it positive, but times this negative makes it negative again, so minus 8 thirds. You can see that these two are the same. And that would make sense because the area on the left of the y-axis is symmetrical to the area on the right. So this would be 16 minus 16 thirds, or 16 minus a third of 16, which would give us 2/3 of 16, or 32 over 3 square units. Find the area under y equals sine x from 0 to pi. Whoa! Okay, this looks really fun. So we know that sine x, is maximum is 1 here, and we want to go from 0 to pi, so let's just write pi on there. And sine starts at its midline moving up, and it's going to reach 1 at pi over 2, and then come back down, and its x-intercept is actually pi. So this will look something like this. And we're looking for this area here. So we want to find the antiderivative of sine x. So that would be negative cos x, because if we're thinking of derivatives, the derivative of cos is negative sine. We don't see a negative here with the sine, so we got to put one here to cancel it out. And the area from 0 to pi is going to be the antiderivative at pi minus the antiderivative at 0. So negative cos pi minus a negative cos 0. And negative cos pi, so cos is our x values, so this will be cos pi is negative 1. Negative 1 times negative there will be positive 1. And cos 0 is positive 1. And I guess I'll just write out all of that. And this will be negative, negative, so plus. So 1 plus 1 is actually 2 units. And that's crazy. Just appreciate what just happened there. We went from 0 to pi, which is an irrational number, and it was exactly 2 units squared in between that curve and the x-axis. Not an irrational number. We want to find the area of that same function, but this time from 0 to 2 pi. And I'm going to just sketch it first so that you can see what's happening. So there's my axis, this is my y, this is my x. The sine function comes up here, down here, and up here. And this is pi, and this is 2 pi. So in the area in between this function and the x-axis here is going to be right here, and also right here. Okay, so let's do that. We have our antiderivative from before, it'd be negative cos x. So the area from 0 to 2 pi would be f at 2 pi minus f at 0. Okay, so that would mean that it's negative cos 2 pi minus a negative cos at 0. Now, cos 2 pi is just 1, so this would be negative 1. And over here, cos 0 is also 1, except this has got a negative negative, which would be a positive. So we end up with 0 units squared. What? Now remember what I was saying before. This is going to be positive area, and this is going to come out negative area. So what happened in this question was, since these two are exactly the same, this just canceled out with this, and we ended up with 0. So if I wanted to get around that, I could do these separately. So I could do the area from 0 to pi, and then add the negative area from pi to 2 pi, because I know this will come out as negative. If I multiply it by negative, it will become positive. But I also know that there's some symmetry here. This area is exactly the same as this area, so I could just say, how about 2 times the area from 0 to pi? And since we did this in the last question, it's actually just 2 times 2, which would be 4 square units. You should be able to find area under a curve. Here's some questions from the textbook. Give them a try, see if you know what you're doing.